Hello and welcome to the Loughborough University Institute of Advanced Studies. I'm Professor Ksenia Chmutina, I'm the director of the institute, and it's my absolute pleasure to welcome Dr. Ilya Chevyrev today, who is joining us for a whole week. Loughborough Institute of Advanced Studies is a home of exciting conversations, of debates, of curiosity, of play, and we normally have discussions and debates about things that are really important, that advance the knowledge and advance the curiosity. So it's wonderful to have so many of you today in the room. There are people joining us online. Just a couple of housekeeping rules. It is a hybrid seminar. It will be recorded, and we have had a quick discussion before the seminar. Ilya has kindly agreed to take questions during the presentation. So if indeed you need some kind of clarification or you want to discuss something, please just raise your hand and we'll manage that. And online, the same, if you have any questions online, please post them into the Q&A section, and Kieran will tell us that there is a question, and we'll try to handle that as well. I think that is it in terms of the, and I forgot to say that, of course, the seminar is recorded and will be released magically in just a few hours after the seminar on YouTube and also as a podcast. Well, without any further ado, I would like to pass to Dr. Alexey Karyapanov, who is hosting Ilya today. Alexey, please introduce Ilya. Thank you.
Thank you all for coming. It's a big pleasure. It's my absolute pleasure to introduce Ilya Chevyrev, my friend and collaborator. Ilya is a very rough person. His main objects of interest scientifically are rough objects with sharp edges, like the Brownian motion, or more generally, solutions of stochastic differential equations or stochastic partial differential equations. These are rough, but they naturally appear in probability theory and its applications. And this is, and even in deterministic dynamics, which is how me and Ilya collaborate. Ilya holds an ERC grant on stochastic quantum gauge theories. And this year he received an award for his contribution to stochastic analysis, the Roloff-Davidson Prize, which is, from what I understand, an award for early career probabilists. And I'm very much looking forward to your talk, Ilya. The stage is yours.
Okay, thank you very much for the very kind introduction and for having me here. It's a great pleasure. It's my first time in Loughborough, so I'm enjoying it very much so far. So yes, as Alexey said, I'm very interested in rough objects. I'm hopefully less rough than the objects I study, but I'll let that leave that judgment up to you. Okay, so let's begin with some pictures. So the things that I'm interested in studying are indeed kind of random systems, which are typically rough, and indeed there's quite a lot of them. So when we study stochastic processes or random, what we call random systems, they tend to have a lot of oscillations that we typically model as being rough. So for example, you can look at trajectories of stock prices and they look like they're not really differentiable functions. So they have a lot of these spikes. Or there's a very popular two-dimensional random surface that people study called Liouville quantum gravity. Don't worry about the name, but as you can see from the picture, it has a lot of these really rough spikes that appear at seemingly random places. So the difficulty with studying these objects is that when we want to study systems like dynamical systems or some sort of a system evolving, general system evolving in time, we often like to analyze these things using differential equations, of which I will present and discuss a little bit more in the coming slides. But these typically differential equations, when we deal with them and study them rigorously or even heuristically, they often require some sort of regularity on functions. So typically differential equations like functions that are differentiable, hence the name differential equations. But these kinds of functions, they're not, or surfaces, they're not differentiable. So this causes a big problem when we try to study them. And in this talk, I'll try and explain how some ideas that enter, especially that have appeared over the last 10, 20 years, of how to handle this roughness. And I'll contrast it with kind of more classical ideas that have appeared before. So let me begin with a very, very old story. The story dates back over 120 years ago. Louis Bachelier, in his PhD thesis, he was interested in markets, and he introduced a very basic model for stock prices, that was the beginning somehow of modern finance in hindsight. Though his work was actually largely forgotten, and then only back in the 60s that people start to appreciate it again. So he said, okay, let me take I'm going to denote stock price by S in the next few slides. And this subscript T, just for notational purposes, this subscript T means the stock price at time T. So this will avoid me. Usually in maths we write with the brackets T as a parentheses, but then there'll be too many brackets if I do that. So he said that, okay, I'm going to model a stock price as with a very simple mechanism. So my stock price at time T plus H, so think of H as a very small number here, maybe like 1 minute. So a given time T plus 1 minute plus H is given by S of T plus some sort of an increment of another process, so B. So B here will be some sort of a noise. Times some parameter sigma, which sigma is like the volatility, so how much uncertainty there is in the market. So sigma is just some real number here, nothing too complicated. So this B that I mentioned, this is supposed to be an idealized, what people call Brownian motion, Brownian noise. So the idea behind this is that this increment B, so how much B changes over an interval of time H, this should be independent of its past. So it should forget effectively anything that has happened in the past. And it should be distributed like a bell curve, like a normal random variable. And the kind of how spread out this bell curve is, the usual kind of bell curve that you see in statistics, depends on how far into the future you look at. So the more you look into the future, the less certain this increment is. And so the more spread out this bell curve. And more precisely, we take BT plus H minus BT to be a normal random variable with variance H. So as H grows, the variance grows. So B is supposed to be a random function of time. So, or in other words, for every time T, it's a real random variable. And so the idea to keep in mind is that this models unpredictable market forces. So there's lots of people all the time, say in the stock markets, there's hundreds of thousands of buyers and sellers, and B models their kind of unpredictable behavior, how much they want to sell, how much they want to buy, and this drives the stock price. So this model is very simple to solve. So for any function B, it doesn't matter whether it's random or not, the stock price is always given by this formula down bottom. So it's given, so S is given by an explicit function of the increment of B over the whole time horizon. Okay, so this is a very simple model. In fact, its motivation was really for introducing this kind of mathematical construct of what people call Brownian motion. Rather than being a realistic stock market. And in fact, one of the issues behind it is that so this model is very, very simple and kind of elegant, but this increment of the Brownian motion, it's a bell curve, and the bell curve has it could be very positive or it could be very negative. So you might have a probability of this number BT minus B0 is very, very negative. And so then if this whole quantity is more negative than S0, then the stock price might become negative. So that's kind of an issue for this being a realistic model. But interestingly, actually, it kind of saw a small revival in 2020 with negative oil prices because of COVID. So this was an interesting phenomenon. So a more sophisticated model in stock prices came about with Black and Scholes. There were two now very famous economists who received the Nobel Prize in 1997, along with Merton. They introduced a model that was more realistic. And so what they said is that, okay, instead of there being, so we're going to keep this idea that there's some noise in the market that we don't know how to predict, there's some unpredictable noise. But instead of just additively contributing to the stock price changing or increasing by sigma times the increment, it's going to increase proportional to the current stock price. And this is a little bit more realistic because in some sense, a stock price requires some choice of units, like it requires currency or something like this. So it requires you to say, is it worth $100 or $10? And then you have to make a sense of what is a dollar somehow, or is it pounds or anything like this. So it's like it requires units. And this kind of choice of stock price is independent of the units that you choose in a way. So maybe the stock price is worth $100, and then there's a big positive innovation, and it will change by $10. Whereas if it was $10 to begin with, it would change by $1. So it would be like, it changes by a percentage of it, rather than like some fixed value. This is somehow much more pleasant, mathematical, much more realistic stock price model. And also, so a feature of it is that if the stock price is very, very low, then the oscillations are also very, very low. And the idea is that it actually never becomes negative. So this you can actually even show that this, and ultimately when we present how we make sense of this model rigorously, indeed the stock price will never become negative, which is good. Okay, and the delta t here plays the role of that very small h. You should think about it like physicists often really like to write this delta h as some infinitesimal quantity. And so in more modern mathematical terminology, we would write down differential equation. So the rate of change of the stock price should be equal to this volatility times the current stock price times the rate of change of this noise that models unpredictable behavior in the market. And so also another advantage of this is that this model is that it gives very clean formulae for financial derivatives. So this model became very popular. Okay, so let's try to analyze what happens in this model, and where do the rough objects that I spoke about come in. So let's, for the moment, forget that B is supposed to be this random noise, and let's just take it to be some sort of a nice function that we understand perfectly well. The simplest function that we could take is just Bt is equal to T. So at every single increment of time, Bt changes by the length of the time that you're looking at. So the increment is always equal to Bt plus H, minus Bt is always equal to H. So in this case, this is a model actually for just very basic interest rates. So for like money sitting in a bank account. And in fact, your solution is going to be given by, the stock price at time t will be given by the initial stock price times exponential of sigma t. Or think of it, maybe this shouldn't be just stock price, it should be money in a bank account. And this is exactly how money in your bank account grows. So this is compound interest. Okay, so this differential equation actually relates to something quite familiar to us. Now, if B happened to be just any smooth differential function, so not necessarily Bt is equal to T, then again, we get a very simple formula, like a small generalization of this. So the generalization is that St is equal to S0 times exponential of sigma B T. Specifically, there should be actually, sorry, Bt minus B0. I guess I'm assuming that B0 is just 0 for this. And indeed, okay, this is after all a math talk, so I want to include a little bit of math details. Indeed, it's quite easy to justify this. So you remember that this exponential function is precisely the function that should, when you differentiate it, you get it back. This is the characterizing property of the exponential function. And then use the classical chain rule to indeed show that this function indeed solves this initial differential equation if B is differentiable. So if B is a smooth function. Okay, so this is just the verification of this fact. Okay, so this on the surface, this now looks like a very simple model. I mean, we look at what B does over a period of time. We multiply it by this volatility, exponentiate, and multiply it by the initial stock price, and that's how we get ST. Okay, but it's actually a little bit it's deceivingly this kind of analogy with smooth functions actually ends up being a bit deceiving. So I'll try and explain this in a second. So what are we going to do? So yeah, so what if now B is this Brownian noise that we expect to not actually be smooth? We expect it not to be differentiable. So let's for the moment take an approximation of our Brownian motion. So let's instead of trying to solve some sort of a differential equation, we solve a difference equation. This is typically how people solve ODEs after all. They take some sort of a step-by-step approximation of the differential equation. So we're going to take like a finite set of discrete points. We're going to divide our interval of time, say 0, 1, into n steps, n little intervals. And in each interval, you look at your stock price at the beginning of the interval, and then to figure out what the stock price is at the next point of the interval, you add to it. So this is the initial point of the integral. You add to it your volatility times your current price times the increment of your function over some spot over this interval. So, and this function that we're going to take as just being defined on the endpoints of these intervals is going to be a symmetric random walk. So I'll show you a picture of this in a second. This is a symmetric random walk on so the z denotes the integer. So it's just so this symmetric random walk has a 1/2 probability of going up by 1 over square root of n and down by 1 over square root of n. And the square root of n, you might wonder where this comes from. It's chosen so that at the end, the total increment has variance 1. So if you do a short computation, you can see that the total increment of your symmetric random walk has variance 1. So to match somehow what we expect to be from the Brownian motion. Okay, and so what we expect is that as n goes to infinity, so as we refine our approximation of this differential equation with a finite difference scheme, well, we should converge to what we should be able to call the solution to the stochastic differential equation, the one that was this exponential of et in this case. Okay, so this is what these random walks. So to demonstrate for what this is doing. So this is a simulation of a random walk with this n being 4. So I divide my interval of time into 4 time steps. And at every time step, I move up and down by 1 over square root of n. So here it's 1 over 2. So we keep and we ascend into infinity. So this is just the pictures for the Brownian motion for the random walks b, not in the stock price. This is if this is n is equal to 10, it looks something like this, and n is equal to 100, it looks something like this. And 1,000, it becomes a little bit more jagged, and then at 10,000, it becomes very rough. So very similar to that stock price, or the FTSE index that I presented at the beginning. So mathematically, it's there's quite a rich theory of these random walks, and people a long time, particularly due to Kolmogorov and Donsker, they realized that these random walks, which are very easy to construct mathematically, they converge to a stochastic process, which is known as Brownian motion. So a well-defined random function. So indeed, we know that these random walks they actually indeed converge to something. So we might expect then that these when we do this very simple approximation of our stock price using these finite difference schemes, it also converges to something. And we indeed expected to converge to that solution of the stochastic differential equation, which was in the very simple context given by that formula, S0 E sigma dt. So okay, so just to remind you, indeed for smooth B, this was the solution to this stochastic differential equation. And yes, and indeed, if you do this scheme, so I fix B and I do the scheme for a smooth B, where the increments of B are not a random walk, but they're just the increments of the function B, then indeed this converges to a kind of a result from classical numerical analysis that this converges to the solution of the differential equation. Okay. So now I'm gonna show pictures of the actual stock price again with like say n is equal to 4, n is equal to 10. N is equal to 100, and you can see that it has these features that I was describing before. So, for example, when the stock price gets small, the size of the oscillation will also get very small. When the stock price is large, the size of the oscillation can also get much larger. And this is 100, and this is 10,000. So this again looks like it has many features of a Brownian motion, but it's not really a Brownian motion anymore because it'll ever become negative, for example, and it kind of the size of the oscillations depends on where the stock price currently is. Okay, so it's sensible to expect that if we're to send n to infinity, then this is going to look like some sort of a random function in the end. So, and, okay, so again, to remind you, what we expect is by arguing with analogy to smooth functions, we expect that ST should converge to this solution. This was an application of the chain rule, but in fact, the answer is actually a little bit surprising. So this expectation is wrong. So in the end, what we actually pick up is something that looks, it has a feature of what we started off with as 0 sigma pt, but we actually pick up another term inside the exponential. So we pick up something that on the surface is actually very surprising. So why do we pick up this? So the precise factor that we pick up is minus sigma squared t over 2. Okay. So yeah. So where did this term come from? So it can. So I won't try and explain why there's this discrepancy between what we expect for smooth functions and what we actually obtain with this random walk approximation of Brownian motion. But there's a justification for it. So it can be guessed by the fact that the stock price is supposed to be at every step, it goes up and down, roughly with probability a half. So it has a same probability of going up and down. So it's what mathematicians like to call a martingale. So it has the same expectation. So over time, its expectation is supposed to stay the same. So what that means in real life is that you're not supposed to be able to make money in the stock market on average. So if you invested into this model, you might have a probability of making money, you might have a probability of losing money, but on average, your earnings will be flat. They'll stay constant. And so, in particular, the average of this stock price should be the same as the average of the initial money that you invested in. So what you expect is that the average of this exponential term should also be 1, because it shouldn't change. And so if we didn't have that extra term sigma squared t over 2, actually this expectation will be quite large. It'll grow with time. It'll grow with time like e to the sigma squared t over 2. So this minus sigma squared t over 2 precisely kills this growth that you see from the expectation of this term. So this is how it can somehow be guessed that this is the thing that you actually see in the limit, and can ultimately even prove. So what the punchline of this is that this Brownian motion, when you try to make sense of differential equations driven by this so-called Brownian motion, it doesn't respect the usual rules of calculus. Okay. So maybe another illustration for another way to see this. So here I've simulated Brownian motion with, I think, a large number of time steps. And what we're going to do is so here I've drawn a kind of a parabola curve. This is a curve which is so along the x-axis is time, and along the y-axis it's square root of time. So it's like you usually see a parabola like this, and then this is like a shifted parabola. What we're going to do is we're going to zoom in on this picture. I'm going to take a box, but keep in mind that the units on the bottom are not in line with the units on the top. But this box is chosen in such a way that keeps the parabola always constant. So I'm zooming in with a factor of I think maybe 1/4 on the bottom, but only 1/2 on the top. Okay. So I zoom in to keep the parabola exactly the same. And the picture that I see is actually qualitatively, at least, it's exactly the same as what I had before. And if I do this again, you'll see that the Brownian motion kind of exits the picture. So here, this is that exit now. So this is really the same. I'm zooming in on really the same curve. Again, it stays qualitatively the same. And if I keep zooming in, again, it stays qualitatively kind of the same. It has the same kind of oscillatory behavior. And so, and what this is called is a fractal behavior. So as you zoom in, the shape of the curve, the shape of the process doesn't change. And kind of this fractal behavior is very closely related to this roughness, because if you had taken a smooth function to begin with, so if this was a smooth function, not a, do I have one? I have one more. If I had a smooth function to begin with, and I did the zooming in, I would actually just see a flat curve at the end. I would actually just see kind of a trivial line. Because if it has a derivative, it will kind of keep getting smushed and smushed and smushed. The Brownian motion has oscillations on every scale. Okay, I even have one more. And one more. Okay. Good. Okay, so how do we actually try to make sense of these stochastic differential? Yes,
Actually, you
Yes.
scale the y-axis with like the square, or maybe the other way around, with the square root of the factor of the other axis.
Exactly, yes, exactly, yeah. So I scale, maybe this is a good way to see it here. So you see that this is like 20 or 30 is the boundary, and then and here I scale I think by maybe 8 or so is the top boundary. So here I go a little bit to 4, and then I go to 7. So it's like a factor of 4 on the x-axis and a factor of 2 on the y-axis. Yeah. So it keeps this parabola shape exactly the same. Okay. Okay, so how do so people actually in maths figured out quite a long time ago, already back in the 40s and 50s, how to make sense of these stochastic differential equations in a rigorous way. So the idea, the main idea of how to make sense of this stochastic differential equation goes back to Ito. He was quite famous in probability theory now for this. So he said, okay, let me write down the differential equation in integral form. This is an equivalent formulation because integrals are integration is the inverse of differentiation. And I'm going to, and I want to make sense of this. I kind of want to define what I mean by this integral. And he realized that you can actually make sense of this integral as a sum of Riemann sums. So it's a limit of Riemann sums. So I'm going to take this exactly like what I did with the random walk. So I look at my current stock price, and then I multiply by my limit of Brownian motion. So he realized that this, if S is any kind of stochastic random process that has sufficiently nice behavior, for example, it doesn't look into the future of the Brownian motion as the key property, then this, as I send my part, so this little n plays the role of the big N before, it's like the size of my steps. As this n goes to infinity, and I look at all of these little tiny increments that I was looking at, this sum is going to converge to something. So it's going to converge to a random process, a stochastic process. So that's what this integral. That's how one makes sense of this integral. And then one essentially solves for S as a solving this kind of integral equation, but really as a stochastic process. So you don't freeze a realization of the Brownian motion. It's not like I give you one realization of Brownian motion and then I solve for S. You need to solve for S knowing the law of this Brownian motion. It's working for. And so this is a very essentially an intrinsically probabilistic construction. And one of its difficulties is that it's actually very difficult to control the solution map that gives you. So if I look at a realization of Brownian motion, and I take these Riemann sums and I solve for S, then what does the solution S really look like? So it's very difficult to control this. Go from a realization of Brownian motion to the solution S. It's easy only to go from the law of the Brownian motion to the law of S, the distribution of S. Okay. And so to demonstrate this, I'm showing here two graphics. So I'm looking at a very closely related stochastic differential equation to what I had before, this stock price model. But I have now two Brownian motions, so V1 and V2. So this 1 and 2, these indexes are they're not powers, they're just indexes. So I have two Brownian motions, and here I've plotted the Brownian motions, one in orange and the other in blue. And these functions, f1 and f2, I don't specify. So previously, these functions were essentially f1 of s was basically sigma s. And here I'm taking a more general function that I don't specify. But I've plotted here two realizations of Brownian motions. So on the left side, I have an orange curve and a blue curve on the top and on the bottom. And the idea is that on the bottom, This is again a Brownian motion coupled to this, or it looks very similar to the one on top, but it has very microscopic differences. And to the naked eye, those two pictures on the top and the bottom on the left, they look identical. So you can't tell the difference between this one and this one. So their difference is very, very tiny at every point in time. But there is a very tiny small difference. And if you solve this stochastic differential equation, essentially that discrete approximation that I was telling you about before, to arrive at some sort of solution, you'll see that the two solutions actually differ very drastically. So the two, so S driven by these two Brownian motions has the trajectory on the right, whereas the S driven by these two Brownian motions has this trajectory, which is very, very different. So kind of on the macroscopic scale, the two what you call drivers, B1 and B2, look identical, but on the ultimately their microscopic differences can be build up to a very big difference on kind of solutions to these types of equations. So the stock prices of these two models will look very, very different.
Yeah, this is capital N equals to 10,000.
Yes, exactly. Yes, this is capital N equals 10,000 exactly. I haven't scaled back time somehow yet. So yes. Right. Okay.
Can I ask?
Yes.
Can a trained eye tell the difference without solving the thing?
Can what?
A trained eye, could it predict I mean, such a difference in the behavior or not?
I mean, for these two, I think not. I mean, I don't think that the pixel resolution allows actually, because the difference lives on scales that I think are below the pixel resolution here. Yeah.
I don't need to.
Yeah, you have to zoom in and increase the resolution a lot. Yeah. Yeah, and then you could tell that they're different. But the point is that like somehow by feeding these two guys into a differential equation and looking at the solutions, it's much easier to tell that they're different than by looking at them kind of front on based on.
And is that due to the Brownian nature of that, or is it do the F1 and F2 just make an unstable system?
No, it's due to the Brownian nature. So F1 and F2 here are smooth and bounded functions, I think. If I recall, maybe not bounded, but certainly smooth. And if B1 and B2 were smooth functions, like so, imagine that they had a derivative and you had some bounding derivative, like the derivative is bounded by 10, then you'll never see this kind of difference of the solutions. So it's really to do with the fact that the roughness of like the Brownian function. Any other questions about this or anything so far?
Are there implications of this for encryption?
Interesting question.
Sorry, I'm wondering if that was something that you did.
No, I haven't thought about it. Yeah, okay. But yeah, an interesting idea, perhaps. Yeah. Okay. So for the interest of time, I wanted to give a rough idea of how one actually handles this. So okay, maybe this will be a little bit for the analytically minded, but I wanted to get a bit of a move on. So let me just be a little bit brief here. I'll throw a little bit of maths out, and then if you don't follow, don't worry, because there'll be a few more kind of heuristics that go afterwards. So let's try and solve a differential equation like this. So let's see what's going on. Let's see if we can kind of restore stability to this solution. So f is a smooth function. So what we like to do with smooth functions is we like to approximate them somehow. So this is called a Taylor expansion. So let's Taylor expand f, and we Taylor expand f around the initial stock price point, so S0. And so the first order approximation of f of st is then is given by this quantity, and where we see the derivative of f, and then we substitute this back into the equation. So if you do this, with a little bit of 1 or 2 minutes of patient computation, you can see that a term comes out that is essentially, it looks like, so we rewrite this differential equation in integral form. And so here we have something that looks like an integral of Brownian motion, so this first order term. And then if you plug this first order approximation for f of s back, you end up with a double iterated integral of Brownian motion. Okay, so this is yeah, just maybe take my word for it for the moment. And then the idea is that, well, if b was a smooth function, then this term, so it's the integral of an integral of b. Okay, so that's kind of the increment of b. Let's just think it this way. But then I integrate it against b again. So it's like integrating b against the derivative of b times ds. And so if b was differentiable, this whole term would be of order roughly t squared. You can think about it like, let's do some order analysis. So this would be a term roughly of order t squared. And then you could, if this term is of order t squared, you can forget about it. So if t is, think of t as a very small number, like the size of my approximation for discrete scheme. Then if this is typically this is of order t squared, so we can kind of forget about this and just use this as an approximation for st. But if this term is big, and for the case of say Brownian motion, this term will typically, or approximations of Brownian motion, this term will typically be of size t, in fact a little bit bigger than size t. Then it can't be ignored. So kind of you need to keep track of this red term. So the very basic idea of how to handle this kind of roughness is not to really only look at the solution S as a function of the underlying noise B, but also as this extra piece of information, the second iterated integral. Okay. Okay. So there's okay. I want to put a theorem up on the board, but let me not delve into it. So basically, the idea is that you can build up a kind of a very nice theory about this, where instead of keeping track of just your underlying Brownian noise B, you also keep track of this extra piece of information, and you require some sort of regularity properties of these objects. So okay, if you're not fluent in analysis, I guess these formulas will tell you nothing. But if you are, then perhaps they'll tell you something interesting. So you require some sort of control on how big these objects B and BT can be, kind of like a generalized notion of derivatives. And then if they're not too large with this notion of size, then you can build you can show that the solution map that maps B to this to say the solution S is actually continuous. So you have some stability. So it's this kind of the philosophy is that you need to not only look at your underlying process, but you need to enhance it with some extra piece of information. So if you look at the previous slides that I gave you before, if for this Brownian motion, for the two pairs of Brownian motions, if you kept track of that extra piece of information, this iterated integrals, they would look very different for these two Brownian motions. So they will be the ones responsible for the differences in the S's. So somehow this extra piece of information, which is like a quadratic function of your Brownian motions, will be the things that kind of restore stability to the map, or responsible rather for this instability. Okay, so the point of this construction is that this pair, so the underlying process B plus this extra piece of information, this iterated integral, is a much simpler object to analyze than the solution to a stochastic differential equation. In fact, you can give meaning to these stochastic differential equations through this kind of theory, and the only place where probability theory enters is in showing that when you take some sort of a convergence scheme like a random walk, that this extra piece of information for the random walk converges to some sort of a limit. So this limiting thing that lives above your Brownian motion. And you don't need to solve then for S in some sort of a space of stochastic processes or something like this. Yes.
So in this theorem, the B basically has regularity slightly less than 1/2.
Yes.
That is disconnected with this picture that you scale by the square root of.
Exactly. Yes. So think of B as a Brownian motion, and one can show that every realization of Brownian motion, this quantity, this supreme over UT, will be finite if and only if alpha is smaller than 1/2. So yeah, and so alpha is equal to 1/2 is precisely that scaling invariance property, and so it kind of in law BT bt minus du behaves like t minus u to the 1/2. And so every realization is a little bit worse than that. So, yeah, exactly. So indeed it's related. Yes.
So say that you chose B to satisfy this result.
Mhm.
If you then went back and like looked at like the stability, like the two pictures of the Brownian motion, would they still be indistinguishable from the human eye?
So you're right. So that's what I was trying to get at before. So these two terms, like the let me go back. Yeah. So this is the picture that you're meaning. Yeah. So if you looked at the so in that theorem there were two components. There's b and the second iterated integral, like a double iterated integral. And for the first component, you have now so you have two Brownian motions, and you have a pair of them. So like you have two Brownian motions here, two Brownian motions here. So for the first component, these two pictures would look identical, but it's for that second one, the second iterated integral, that the second iterated integral of this pair of Brownian motions would look very different from the second iterated integral of this pair of Brownian motions. And they're the ones that are responsible for this big difference over here. Okay. Yeah. Okay, so so let me move on to so I think that's all the maths that I'll have in the talk. So let me now move on to kind of a few places where these ideas have flourished. So this idea is, I mean, you can see the date of the theorem. It's from 1998, so this is very old. Lyons was I think it was at Imperial at the time. The British mathematician, I think, now back in Imperial actually. So one of the fields where these ideas have taken off more recently, so over the past maybe 10 years, is stochastic partial differential equation. So I was always talking previously about just things evolving in time, but it's very interesting to look at stochastic processes evolving in time and space. So generally, the way that we model equations, model randomness frequently through some sort of an equation. Like here, I take a class of equations which are like heat equations. So this is supposed to be the leading equation is a diffusion equation of energy. So if you're not familiar with it, think of it as like diffusion of heat through some sort of a surface. But it's perturbed by some sort of a nonlinear function. So psi here is supposed to be something like a random function. Okay, there's a few examples of this, but I'm going to focus on this example of crystal growth. So it's on the next slide. I'll present this equation in more detail. So it's called the Carter-Parisi-Zhang equation. When trying to solve these equations or even approximate them, we run into the same problems as we did before. So we expect these solutions if the noise is somehow very rough. So think of this psi as maybe the derivative of the Brownian motion we had on the previous in the previous slides. Then these equations have terms that are, they might have nonlinearities that require us to make sense of maybe multiplying distributions, which analytically is a ill-defined procedure. So this roughness of the noise causes a lot of difficulty in solving these equations. So yes, let me expand on this example of Carter-Parisi in Zhang. So what these three physicists proposed back in 1986 was a mechanism for growing interfaces. So H here is supposed to represent the height function of some sort of an interface. So like I don't look at the height function, but maybe the distance function from some sort of initial point. And they wanted to say, okay, I have some sort of maybe I have some sort of droplets so maybe this is supposed to be like a crystal growing, and this crystal, as it grows out, it encompasses kind of new material, or maybe I have droplets that go and join the crystal, but these droplets come in at random times. They attach to the crystal at random locations and at random times. This is this random noise that fluctuates the system. But at the same time, I want like kind of my interface, this height function to kind of smoothen out. It doesn't really like to be very rough. So there's some sort of an energy that causes it to become smoothened out. That's this diffusion term. So I don't expect anyone to kind of see right from the naked eye that these are supposed to be responsible for this diffusion. For me, certainly it wasn't clear, but kind of I just want to illustrate that in this equation, kind of every term has a particular meaning. And then this final term, so this is the derivative of h squared. This term is supposed to be like a growth term. So it's like if your derivative is very large, then you have a very large surface. So you have much more chance of particles attaching to that surface. If your derivative is very small, then the surface area's exposure to kind of the other interface is much smaller. So you expect much slower growth in the place where your surface is flat. And so they propose this kind of nonlinearity to model this. And actually, in experiments, indeed, you have very good behavior. You have very good matching experiments. Like if you solve this equation, you look at its fluctuations, like you look at how this function looks like, and for many actual growing interfaces, it matches this matches the solution to this equation. Okay, so I had an image here that I wanted to play. So this is an illustration of this growing interface. So the first one is an illustration of the noise. So this is random blocks falling down according to just a purely noisy system, and they're totally independent of each other. So they just drop at random points. This is like that psi term, the Greek letter psi in the previous slide. And you can see this is creating sort of a very rough, very independent in time interface. So this is like the driving noise, if you like, psi. And this is then the solution to the equation, or a discretization of it. So this model, what these blocks are doing is that this is a model that is supposed to mimic this equation. Let me just go back so you can see it a little bit better. It's called the sticky block model. So as the blocks fall, if they touch another block, maybe I should do it here. If they touch another block on the side, they stick to it. So yeah, so they have sticky sides. And if you do this, then the solution looks very different from the kind of pure noise. In fact, it picks up a lot of it has a lot of holes in the center, but the interface becomes actually a little bit smoother. So the interface now, if you could kind of make sense of it, it's a bit smoother, but it's still very rough. So this is supposed to be an approximation to that solution of that equation. So I just wanted to give you a flavor for what kind of processes this equation is supposed to solve, to mimic. Okay, so so there was a big mathematical challenge as to how to actually make sense of what you expect the limit to be. So that the solution that gives this equation. So this was finally solved by, in mathematical terms, somewhat recently, still about 10 years ago. But obviously not so recent in real terms. And the idea was that one needed to kind of make sense of this stochastic differential equation in a way very similar to what we did with this what I discussed with the rough path philosophy. One needed to kind of keep track of not only this noise term, but kind of nonlinear functions of this noise term. And an extra feature that we didn't see before was something called renormalization. So on the block model, renormalization comes from the fact that if you let the simulation run and you didn't rescale time in any way, then the speed at which your blocks kind of start increasing goes to infinity. So they kind of start where this interface starts going faster and faster and faster. And so you actually need to kind of subtract this average speed off to see some sort of an interesting fluctuating behavior. And while that's kind of an easy heuristic to kind of describe, it's actually very difficult to make sense of this mathematically. So kind of one needs to be able to, from this equation, to really study it properly, one actually needs to subtract from it this kind of like an infinity term and make sense of what that even means. So yeah, for this work, and actually for a generalization of this work that was able to handle out equations, actually Martin received it from the Fields Medal in 2014. This was kind of considered a very important development in the field. Yeah, so there was kind of so building on this, there was somehow a bit of a revolution in SPDs, and stochastic partial differential equations. Let's see. How do I make this? Yeah, I'm gonna make it full screen. How do I do that? Wonderful, great, yes, great. Okay, so let me wrap up. Yeah, so now there's, okay, the slide is just supposed to say that there's a kind of a way to handle very general equations now. So there's a general mechanism that given a stochastic partial differential equation of this type, you can take smooth approximations of the noise, and provided that you renormalize it, you kind of get a sensible limit in the end. And the steps are very similar to what we had before, except with rough paths, there's a probabilistic step of somehow building an object. So you're showing that approximations of your noise and sort of nonlinear functions of the noise converge to some sort of a limit. This was like to make it as G psi. So G is the, say, convolutional with the heat kernel. So the solution to just the linear equation without any nonlinearities. Squared, so this plays the role of like that quadratic term that we saw before for Brownian motion. So you need to show that all of these objects kind of exist for nice approximations of your noise. One big difference with rough paths is that, again, you need this renormalization, so you can't just keep track of the naive definitions of these objects as we typically could with ODEs. Then there's a purely analytic step of mapping this object to the solution. This is continuous now, and exactly like in rough path theory. And then there's sort of a final algebraic step, which is to identify how you should actually renormalize the PDE in order to obtain that. So there's these counter terms that one has to insert. So these counter terms are very familiar in physics, actually, especially in quantum field theory. They play a very similar role here. Okay, so I wanted to give one more example where this appears in fast flow systems, which is what Alexei and I work on. Yeah, let me be very quick here. So another place where this philosophy behind keeping track of not just your noise but of extra data comes in is when analyzing fast flow dynamical systems. So imagine that you have an ergodic dynamical system. So this is a fast component that revolves on some sort of a space called it here omega, and it drives a difference equation, same exact difference equation as I was looking at before. So you look at the previous time point, and I add some sort of a noise that depends on my fast component. So this V is some sort of a nice function from my space to RD, and B's here is just a matrix that depends on the point Y. And then I'm interested in whether this slow dynamic Y converges to something if I rescale time appropriately. So then one can rewrite this as a differential equation, or rather kind of as a difference equation where this X played the role of the B before. And now, but the difference is that this is now a deterministic kind of system, and the only randomness comes from the initial condition of the fast component X0. And so, kind of, what previously a lot of people studied this problem, and they kind of treated Y and X together kind of as one big object. This was very similar to how Ito solved stochastic differential equations, kind of like intrinsically probabilistically. And it was about 8 years ago or so that one of our collaborators in Melbourne realized that you could apply this rough path approach. So him and his colleague David Kelly realized you could apply this rough path approach to this problem. And it gave kind of simplified proofs and simplified methods quite a lot. So what kind of essentially what you have to do is keep track of this X as in the space of rough paths and show convergence there. And then with a purely analytic method, this convergence then transfers to Y. So an example that we were looking at was a so-called billiard system. Example 2, because I think I had example 1, but I deleted that, so it's just example. So you have some sort of a billiard system with a table, and this transformation T is the point on the table and the angle at which the ball will hit next. And if you look at this, these so-called, so you have these Birkhoff sums. If you look for nice functions, these Birkhoff sums look like they have certain trajectories. And an interesting feature of them is that they have these like kind of places where you have very large oscillations. These oscillations come from the fact that sometimes we've designed this table in such a way that it has a big cusp. And sometimes when the ball flies into the cusp, it oscillates a lot inside the cusps, and the Birkhoff sum changes by a huge quantity in this when it flies into the cusp. So that's the response. That's why you get these large oscillations. And then if you look at an observable that's two-dimensional, you get kind of oscillations that look like kind of very interesting features. So you should keep in mind that like these Birkhoff sums go from one point to the next in essentially infinitesimal time. So they traverse these trajectories very, very quickly, and then they kind of like stay in one place and they traverse the trajectories again very quickly. And then for the slow dynamic, if you looked at what it converges to, it has a very kind of strange behavior. So it has a seemingly strange behavior because it also has these jumps, but they don't really look like, it depends on the shape of the D, of course, but the non-linear function. But you see it's kind of has a kind of a strange, it's not immediately clear how to make sense of what this limit should be. And it turns out that here you can also apply rough path philosophy, but in a slightly different way. So you don't want to keep track of only these Birkhoff sums, but you want to also kind of enhance it with some extra data. And this extra data in this situation is these extra excursions, like these butterflies that we saw in the previous on the previous slide. So you want to keep track that like when the process jumped from one point to the other, because it kind of traversed this in infinitesimal time, it becomes it looks like kind of like a butterfly shape. And if you do, so if you enhance your data with this extra, you enhance your process with this extra piece of data, you can actually solve this stochastic differential equation that behind this that governs the slow process, and show it converges in some sort of a sense. So it converges in some you can make sense of this kind of stochastic differential equation, if you like, driven by this process with the enhanced data. We call this a decorated process. So it's kind of maybe at first surprising that one can use this rough path idea of enhancing your data with some extra piece of information, but in quite a different way here than what it was before. Okay, so yeah, so to summarize this, I would say that the core idea behind this study of rough objects with called rough analysis is to separate analysis and probability. And you keep track of your basic underlying process, but also some additional data that's needed in order to analyze the system that it interacts with. So it's built a relatively kind of new, with new in quotation marks, because it's 20 years old. It's kind of still finding new uses. Develop a new calculus for rough objects. It has nice extensions to stochastic partial differential equations. And it has kind of lots of connections with math physics, as I demonstrated, with dynamical systems, but also with it's on a lot of uses in numerical analysis, finance, filtering, biology. So at the moment, it's still a very interesting growing field, I would say. Okay, so thank you very much for your attention.